Hello again, this is Mr. V. Hill. Today we're going to be talking about dividing polynomials. But before we get to that, we're going to first recall something that we learned quite a while ago, and hopefully you all remember, but just long division with integers. Because it's basically the same thing as what we're going to do with polynomials. Now, first let's consider this problem of just 2076, say, divided by 63. Now, with division, I normally say that there's no such thing as division, but that's only when we actually have multiplicative inverses, like with the rational numbers or the real numbers. With the integers, we don't have any fractions, so we can't take the reciprocal of anything. So we do have this division operation, and it basically works, as you know, with long division. So the way we set this up is we take 2076 and put it in our nice long division symbol. 63 is out here. And we see, well, how many times will 63 go into, well, the first few digits that we need. Obviously, 63 doesn't go into 20, but it will go into 207. And it'll go into that 207 3 times. So we put a 3 there. And then we multiply the 3 times the 63 and put that down below here. So 3 times 63 is, of course, 189. And then we just subtract straight down. And 207 minus 189 leaves us with 18. And then we bring down the next digit, giving us 186 down there. Now we see how many times 63 goes into 186. Well, that goes twice. And 2 times 63 we put below here, that's 126. And we subtract straight down, and we end up with 60. And now since 63 cannot go into 60, well, we just put this up here because that's going to be our remainder, if you remember that. Now, one thing about this here is that these different numbers in here do have names. So underneath the long division mark, we call that thing the dividend. Hopefully you remember that. The 63 over here is the divisor. This 32 up here is the quotient. And the 60 that we ended up with down here or up here with the R there in front of it, that is, of course, the remainder. Shows up both spots. Okay. And actually, this thing does have a special name. And it is called, well, this is one example of this special thing that is called a Euclidean algorithm. It's named after the Greek mathematician Euclid, and usually if we name something after a mathematician, then it's usually pretty important, and it actually is. We're not going to go into it too much, but it's neat that the polynomials actually do have this same Euclidean algorithm as the integers do. But the bigger thing about this whole process is what it really means. And basically the idea here is that the dividend is equal to the divisor multiplied by the quotient plus the remainder. That's what this whole thing really means. So the basic idea here is, for our example, is that 2076 is exactly equal to 63 times 32 plus 60. And of course, you can check that out if you want to. However, another thing we can do, and if we want to actually show this division within the equation, if we just divide both sides by 63, well, now we have this ratio of 2076 on top and 63 on bottom. So we could rewrite this as 2076 over 63 is equal to, well, we're going to distribute this dividing by 63 to both of these terms. So that would be 63 times 32 over 63 plus 60 over 63. And now these 63s cancel out within that term. So we have that this fraction here, 2076 over 63, is equal to 32 plus 60 over 63. If you want to see that in the calculator, it's pretty easy to do. If we did the actual 2076 divided by 63, we get 32.952 whatever. Well, that 32 here is exactly that 32 there. And it should be that this extra bit after the decimal should be 60 divided by 63. Yep, it's the exact same thing. So that's really the big point of a Euclidean algorithm, is to be able to write a ratio in this fashion, or even writing it in this way up here. Doesn't really matter. Both are very useful. Okay. Now, let's do the same thing, but now with a polynomial. So, long division with polynomials. We'll just do a quick little example here. Call it example 1. Let's try this. Let's say x cubed minus x squared minus 34x minus 56. We're going to divide that big thing by a smaller polynomial, x minus 7. We're going to set it up in the exact same way as this long division with integers here. We take our dividend, x cubed minus x squared minus 34x minus 56. I'm going to divide that by x minus 7. So the first thing we do is we don't want to go with the whole thing right now. We're just going to focus on this first term. And we want to multiply x minus 7 by something so we get pretty close to x cubed minus x squared and so on and so forth. So of course the thing that's going to work is x squared, because x times x squared gives us x cubed. So what we do is we put a little x squared up here. Now we multiply this x squared times the divisor and write that down here. So x squared times x gives us our x cubed, and x squared times negative 7 gives us a minus 7x squared. Now just like we did over here, we're going to subtract. The x cubed minus the x cubed, that's of course 0. Now be really careful with your negatives here and the subtractions. We really have a negative x squared, and we're subtracting from that a negative 7x squared. So subtracting negative 7x squared is really adding positive 7x squared. So this is going to be negative x squared plus 7x squared, leaving us with 6x squared here. Very easy to mess up and lose a negative sign in there. Now we bring the next term down, minus 34x. Then we ask ourselves, well, what do I need to multiply x minus 7 by to get a leading term here about 6x squared? Well, of course, that's going to be 6x. So we multiply 6x times x minus 7 and put that down here. 6x times x is 6x squared minus 6x times 7 would be 42x. And now again we subtract. Negative 34x minus a negative 42x, that'd be adding 42x here. So negative 34 plus 42 leaves us with 8x. Now we bring this down, minus 56. And then we see, well, what do we multiply x minus 7 by so that we end up with something about 8x here? That's, of course, 8. So 8 times x minus 7 is 8x. 8 times 7 is 56. And when we subtract, of course, this leaves 0. So that's our remainder of 0. Great. So actually x minus 7 divided evenly into this big cubic polynomial. Or, so what this really means is we can rewrite x cubed minus x squared minus 34x minus 56 as the divisor x minus 7 times the quotient x squared plus 6x plus 8 plus the remainder of 0, but of course we don't need to write that plus 0 out there. And what we might notice is that, oh, this thing right here, the resulting polynomial, the quotient, that factors. Kind of lucky for us. That's not always going to happen, but in this case it does. And so the whole thing is actually x minus 7 times, well, we need two numbers that multiply together to give us 8, but add together to give us 6. That's, of course, 4 and 2. So that's x plus 4 times x plus 2. So this is just one way of factoring a larger degree polynomial. Like here we took this third degree polynomial and we wrote it as first a linear, which is degree 1, times a quadratic, degree 2, and then we factored that as 2 degree 1s. So we have 3 linear factors when we multiply them together to give us this cubic. But nicely now, so if we want to know the zeros of this function, they show up in our factors. So the zeros of y equals x cubed minus x squared minus 34x minus 56 are going to be the things that make each of these linear factors 0. So in order to make x minus 7 0, x needs to be 7. X plus 4 equals 0 means that x has to equal negative 4. And x plus 2 equaling 0, that says that x has to equal negative 2. And we can even check that if we wanted to. We can graph the cubic. So we just type in x cubed minus x squared minus 34x minus 56. And if we graph that thing, oops, my window's off a little bit. Kind of looks all right, but let's go back to Zoom Standard. A little bit better. Okay, it looks a little goofy, but we're not seeing a big portion of this graph. The way cubics work is the graph is going to start low, come up high, cut through the x-axis right here. That is our 0 of x equals negative 4. It turns around, comes back down, hitting the x-axis at negative 2. Then it's going to come way down here and then turn around and come back up until it finally hits the x-axis again at 7. So one little application of this long division here. But let's look at another example and another way we can use this. We'll call this example 2. Let's suppose we take x squared plus 2x minus 15 and divide that by x minus 2. When we set up our long division here, x squared plus 2x minus 15 divided by x minus 2. Now we need to multiply x minus 2 by something to give us an x squared term. That's of course going to be x. X times x minus 2 gives us x squared minus 2x. We subtract. X squared minus x squared is 0. 2x minus a negative 2x is going to be a 4x, because subtracting a negative is actually adding a positive. Bring down the next term, minus 15. And what do we multiply x minus 2 by? So we'll get a term of 4x there. That would, of course, be 4. So 4 times x minus 2 would be 4x minus 8. And we subtract. 4x minus 4x is 0. Negative 15 minus a negative 8 is going to be negative 7. So that's our remainder. So what is this actually telling us? What it's telling us is that x squared plus 2x minus 15 is actually equal to the divisor, which is x minus 2, times the quotient, which is x plus 4, plus the remainder of negative 7. And if we multiply this all out and then add and simplify, we'll get right back to here. I invite you to check that. Or, alternatively, what we could do is, if we really want to see the ratio here of this quadratic over this linear, if we divide both sides by x minus 2, and then if we distribute this dividing by x minus 2 to both of these terms in the numerator, we see that x squared plus 2x minus 15 all over x minus 2 is equal to x minus 2 times x plus 4 over x minus 2 plus negative 7 over x minus 2. And of course what's going to happen here is this factor of x minus 2 on bottom is going to cancel with that factor of x minus 2 on top, showing us that x squared plus 2x minus 15 over x minus 2 is actually equal to x plus 4. I'm going to leave that in parentheses just for the time being, plus negative 7 over x minus 2. Now, how we want to look at this is usually probably best seen in the graph. And so let's put that in. Now remember, when we're typing this in, we're going to need parentheses. Sorry about that.
Jesse Buchanan, please come to the main office. Jesse Buchanan, please to the main office.
So put parentheses around the numerator. X squared plus 2x minus 15 divided by, in parentheses, x minus 2. If we graph that, that looks a little strange. But let's zoom out a little bit. I'm just going to change my window. Let's go from negative 20 to 20 on both axes. See if we can see this a little bit better. Oops, I messed up a little bit. Oops, that's why. Why max it? 20, not 2. Okay. So over here, we got what looks kind of like a fairly straight line. Same thing up here. But there's some weirdness going on right in here. Well, that weirdness comes out of this whole dividing by x minus 2. The whole idea here is if x is 2, then we have 2 minus 2, or 0 in the denominator. You can't divide by 0. That's what's going on here. Here's x equals 2. We have some really strange stuff going on here. We'll talk more about that later. But away from that area, here again, we can still, over here we can't have x equals 2. But away from x equals 2, this thing is going to kind of not matter much. Because as x gets really, really big, the denominator is going to be huge here. And anything divided by something huge is something very small. So everywhere away from x equals 2, this graph, this whole ratio here, which we have graphed, is really going to behave like x plus 4. So let's put that in here just so you can see that. A second function of x plus 4. Now when we graph that, we're going to have the original equation, and then this line is going to go right through it. Oh, okay. See that? The line stays really close to this graph, and then it just keeps going straight where the original graph started blowing up to infinity. And same thing over here. The graph shooting off down to negative infinity here, but the graph just keeps getting closer and closer and closer to that graph of x minus 4, excuse me, x plus 4 right there, which is kind of a neat thing. and we'll talk a lot more about that later. But first, in class, we're going to get a whole bunch of practice doing some long division like this, because long division's fun. See you in class.